Hi there. Thanks so much for showing up for your learning. We're going to briefly review the lesson on an introduction to inequalities. So these types of things are, work very similarly to equations, but instead of something like 3x equals 18, we're going to be interested in cases where things like 3x are greater than 18. In that case, you'll find that x is greater than 6 is what we're working on. All right. The main thing is notation and getting some of the notation under our belts. So we're going to be using these types of signs. X is greater than 2, or x is less than 2, or x is greater than or equal to, or less than or equal to. And we might represent these things on number lines. It's very useful, actually, to demonstrate where things are above or below the line or things like that. When we have closed dots on the number line, that means we are including a and b as possible values of x. They are less than or equal to, or greater than or equal to x. And in interval notation, they're noted this way with square brackets. The square bracket means include a. The rounded bracket means exclude a. Similarly, the open dot means exclude that point. We can also have things go off to infinity, like here, negative infinity not inclusive to be inclusive would be noted this way on the number line. Okay? All of those values that are b or less. This one is all the values that are greater than a, greater than or equal to a. So a or greater. But if we have not inclusive, that's greater than a but not including a. This is all the values that are less than b but not including b. Okay? Now, note that infinity is never included because we're never using that square bracket there, because you never arrive at infinity, so we don't need to include that value. It's not a number, it's a concept. Let's keep going. Okay, so representing on number lines, here, open means don't include, closed means include, please. Okay, so this would be the same as saying x is greater than or equal to -1. This one is saying x is strictly greater than -1, but not equal to. Okay, so the tricky ones here are things like when we have, things like, well, these two intervals, they don't overlap, they don't have an intersection, but we want to include both. Like we're just saying x can't be 1 or 5, or indeed between those values. But anything like where x is less than 1 or x is more than 5, these are fine. Okay, that would be notated like that on a number line, and we'd use the word or if we were writing it out in inequality notation. If we have stuff that's like a mixed bag here, there you have x is less than 1 but not including it, and x is greater than or equal to 5 including it. Like that, right? But what would it look like if this is your preferred notation of choice? We say it's the union between the two sets. So this is the same as, you'll recall, x is less than 1 or 5 is less than x would be how I might write it otherwise, and written in interval notation it looks like that. The u means union of those two sets, or those two intervals, so it's taken together. Similar to or, okay? And then over here, like we want both of them to be inclusive, so we include these with square brackets, but we never include the infinity, so it's always round brackets. All right, so let's write this in interval notation. Don't mind if I do. That would be, to inclusive, all the way to positive infinity, not inclusive. Inequality notation is x is greater than or equal to 2. And that's it. Okay. This one here, we have negative infinity 3, not inclusive in both cases. The union of that with 6 to positive infinity. Okay, inequality notation would be x is less than 3, or 6 is less than or equal to x. This one, we would go -5, 15, include the 15 please, or minus 5 is less than x, which is less than or equal to 15. Both are fine. Now we want to graph it? Sure, again, that's easy. Oh, made an error already. Open dot, go that way. That's all of the values where x is less than 3, not inclusive. How about this? Let's go orange for fun. I like a little fatter for these. Not that fat. Come on. Like that. That's good. So minus 4, we're including that. So we're going to color that in. Go all the way to 2, and we don't include it. Okay. Now solving, there's a trick. All right. Let me walk you through why the trick exists. Watch this. If you have something like 10 is less than 11, I think you'll agree that's true. I can even add to both of these and get something nice like 15 is less than 16. That's still true. Watch, I could multiply both by 3. 45 is also less than 48. But watch what happens if I multiply by negative 1. Negative 45 is less than negative 48? That's not true. So the thing here is whenever you multiply or divide by a negative, then the direction of your inequality has to change whenever you do that. Okay, so otherwise you're moving terms across in exactly the same way. The only exception is multiplying or dividing by a negative value. At that time, the inequality symbol has to change directions. Okay, if you have like 5 is less than 10, well, negative 5 is actually greater than negative 10, and this still tells the truth. Okay, so we're going to see where that shows up. Let's say over here I do this inefficiently and I take away 5x from both sides. Okay. That should be fine. I should be able to retain the same flow. So I have 4 is less than or equal to 3 minus 8x. And then I take away 3 from both sides. Because I'm adding and subtracting, no problems. I don't have to worry about that. And then here, negative 8x is greater than or equal to 1. If I were to divide by negative 8, I have to change this one's sign. Okay, so the direction, sorry. So I have minus 1/8 is greater than or equal to x. It changes direction in that moment where I divide by minus 8. So if I were to graph that one, maybe I call this minus 1 on 8, and this is 0, and this is 1, 2, 3, 4, 5, 6, 7, 8. 1's like over here. It's all of these going that way. Because x, oh no, sorry, it's less than. So x is going the other direction. X is all of these. X is less than or equal to minus 1/8. Ugh, that's weird. Okay, cool. This one over here, suppose I take away x from both sides. 7x is greater than 2, and x is greater than 2/7. At no point do I need to change the direction. So I might say this is here 2/7. Here's 0. And then here's 3, 4, 5, 6, 7, that's 1. And x is all of the values that are greater, but not including 2/7. If we have compound inequalities, best to just keep them all in order that they're in and do your inverse operations very carefully. So here I get out my inverse operation pen and add 8 to all of them. Adding or subtracting never changes the direction of the inequality, so we just do that. And then we have 4 is less than 2x is less than or equal to 18. And no problem here. I can go ahead and divide all of them by 2. That's okay as well. And because I'm dividing by a positive number, no alligators shift direction. So this one would be, oops, don't include 2, 3, 4, 5, 6, 7, 8, 9. Do include 9. And it's all of the ones in between 2 and 9. Or written in interval notation, it would be 2, 9, round square. Over here, let's subtract 7 from both sides. Subtracting 7 does not change the direction of the inequality, so we have minus 12 is less than or equal to minus 3x is less than or equal to 36. But then when I go ahead and divide all of them by minus 3, I must remember to shift the direction of these two. Okay. So that would give us 4 is greater than or equal to x, which is greater than or equal to minus 12. Okay. And in my experience, minus 12 is less than 4, so that still works. So we have here include minus 12, include 4. This is 12, this is 4, and I don't know what my scale is there, but I don't care. All of those points all still works. Then we get into what about the union and the intersection of different things? The intersection is to say both things must be true. We want to choose something from A that's also in B, or like what's in A and B, then it's just 10. Okay? This is how you write the intersection of those two things. Okay? But if we have the union of two sets, that's where we're just putting the two sets together. So then the union of these is 10, 11, 12, all of those, plus those two. Not this one twice, it's already there in the first one. So that's the union. And A union B is those. So that means X is either in A or in B. Okay, so here, if A is 1, 2, 3, 4, B is that, and C is that, let's take a look. A intersection B is what's in that and in that. Well, that would be only 4. It's the only number that appears in both. A union B is 1, 2, 3, 4, 9, 14. So the union is very different than the intersection. C union D, well, C is all of the even numbers, and D is all of the odd numbers. So this is, the union is just 1, 2, 3, 9. It's all of the digits from 1 to 9. A intersection C is 2 and 4. And C intersection D is the null set. Nothing there. There's no number that's both even and odd. Okay. So we want to graph this one, the union of those. Well, we have minus 2 inclusive, all the way from negative infinity, and 3 all the way to positive infinity, like that. If we have the intersection here, well, 3 is the upper one on that way, and then minus 1 is the lower one on that way. So we'd include both of those, but we want the intersection is just the overlap between those two. This one was like that, right? And this one was like this. So the only place they overlap is there and there. So that's why I wrote this. And then let's solve these and then graph our solutions. So here, minus 5 from both sides. X is greater than 1 and, so we must be both. 6x is less than 18, or in other words, divide both sides by 6. X is less than or equal to 3. So this is 3 to 1. There's 1 there. It's that. Okay. X is greater than 1 and x is less than 3 is this. Okay. Over here, subtract 2 from both sides. You have x is less than or equal to minus 5. Or we add 5 to both sides here. X is greater than 3. All right, so this is minus 5 back here. And it's all of those. But then we have 4, 3, 2, 1, 0, 1, 2, 3. Not inclusive. All of those up there. 3. Okay, and I don't really worry about your scale. Don't worry about it. Okay, so you can practice these to get a little bit more practice. And try these practice problems. Go!